Hello and welcome back to the channel. This is the second 2D tutorial in our Ansys Fluent Academy Beginner CFD series. In this lesson, we will simulate SCD incompressible laminar flow in a circular pipe, covering everything from geometry creation in SpaceClaim to meshing in Ansys Meshing to setting up, running, and post-processing the simulation in Ansys Fluent. We will work in axisymmetric mode, which means we only model half of the cross section to save computational time. The pipe length is 8 meter, and since we are modeling the radius, the height of our 2D geometry is 0.1 meter, corresponding to a full pipe diameter of 2 meters. The inlet velocity is 1 meter per second. You can see here. And then density is 1 kilogram per cubic meter, and the dynamic viscosity is 2e-3 kilogram per meter second. At the outlet, we will set the static pressure to 1 atmosphere, and the pipe wall will have a no slip condition. Using these values, the Reynolds number is 100, which is far below the 2300 transition threshold, confirming that the flow is laminar. As the flow enters the pipe, the velocity profile is initially flat. You can see in this contour plot. Viscous effect from valve gradually show down the fluid near the surface while accelerating in the center. You will see this in the velocity contour where the color pattern changed from uniform to curve, and in the velocity versus x position plot, which is an xy plot along the center line, here in the center line of this pipe, where the velocity increase near the entrance, and after a certain distance it reaches a constant value. This is the point where the flow becomes fully developed. It's roughly here, meaning the velocity profile no longer change along the pipe's length. So let's get started. So to start, we will work with the workbench and use a system called the Fluent here. So to do so, I just drag this Flow system and drop here. So I can call this one as Laminar Pipe Flow for the project name. So you can see in the first video, if you go to the first video, you can check and be familiar with different parts of the workbench there. So to create our geometry, we will use Ansys SpaceClaim, which is a default software and geometry modeler here in the workbench. There's a video in our channel that explains how we can change this default setting, so you can use that video. But for a start, I will just click on the geometry and then change the analyze type from 3D to 2D. Then I can right click and select the new SpaceClaim geometry, or starting by double click on the geometry, and you will see in the status bar that SpaceClaim is starting to open. So we will wait to open the SpaceClaim. Okay, so before I start, I want to mention again that the purpose of this playlist is to help beginners start learning CFD simulation with Ansys Fluent from scratch. It is important to follow the videos from the very beginning, because in the first video, I explained many fundamental details that I won't repeat it here. Instead, in this tutorial, we will focus more on new concepts and steps that build on what we already covered. Now, let's move into SpaceClaim to create the geometry. Since this is an axisymmetric problem, we only need to draw half of the pipe's cross section. So the full pipe length is 8 meters and the diameter is 0.2 meters. But because we are modeling only the radius, the height of our geometry will be 0.1 meter. So I will start by creating a rectangular that represents the fluid domain. The length will be 8 meters along the x-axis, and the height will be 0.1 meter along the y-axis. So we need to start our sketch. We are now in the sketch mode. So we will go to the sketch and select the rectangular. Then we can select our sketch plane, which is XY plane. So I will select this one. Then I will bring the mouse near this uh, this point. So now I can select the XY plane. And if I select here, we call it a plan view. If I click here, so we will move to XY plane. So now I can start this rectangular from this origin. I will click here. And then as this is in the millimeter, I need to change the unit. So I will first escape. So to change the working unit for the length, for example, you can go to the file and then SpaceClaim options here. So in the unit part here, you are working in metric type, and so you can change the millimeter to meters and then press OK. So again, I will go to the rectangular tool, select the origin, and this time as you can see, I can uh, work on the meter unit. So first of all, I need to enter the length value. So this is 8 meter. So I just type 8 and then press tab key on the keyboard, so I can zoom a little bit. If you change the position of the mouse, so you will see this rectangular can create in different directions. So I will just select this part, bring the mouse here, and just after pressing tab key, I just write 0.1 meter as I explained. This is like a radius, and then press enter. So now this is the sketch that we have. So if I simply just exit, use this end sketch, if you go to the structure, you will see that you have a surface here, that this is actually your domain for your 2D analysis. So if you want to be sure about the length and the dimension and the radius, so you can go to the measure tab, select the measure, and if you select here, for example, this line, you will see the length is 8 meter. And if I click in this edge, you will see the length is 0.1 meter, our desirable length. So I can press escape and exit from this actually tools. So the next part is to define our boundary condition here. So if we check here, so you will see the boundary condition here. The name is inlet, here is outlet. This top is wall, and we are modeling this line now in the geometry. So this is center line. So I can go again in the SpaceClaim, and to define your boundary condition, you can go to the group tab, and if you select this edge, for example, so you can use this create name selection, or press Ctrl G. So I will select this one and create name selection, and then I will write it as inlet, press enter. So this boundary condition has been defined. So I can go to the right side of this geometry. I will select this one. This time I will use Ctrl G on the keyboard, so you will see we have a new group. So I will call it as outlet. And this time I can simply select the top edges here, this one, use Ctrl G again, and call this boundary as wall. And finally, this is the center line that I can select and use Ctrl G again and call this one as center line. Okay, so now we have defined our geometry and the boundary condition. So everything is ready to move to the next part in the Ansys. So to move to the Ansys Meshing, you don't need to save your geometry file here. So you can just simply close the SpaceClaim because we are working in the workbench. So it will be saved in a temporary folder. So I will close the SpaceClaim. And if I go to workbench here, you will see this task has been done. So the geometry is ready. But if you close the workbench, it is an unsafe project actually. So you will lose your geometry or everything that you have done here. But if you save this project, you can use the save, and I will go here and save. I will call it as Laminar Pipe. So it is Laminar Pipe, for example. So I will save this project. Okay, now we can use the Ansys meshing to generate the mesh here. So I will double click on the Ansys meshing. You will see in the status bar that this meshing is starting to open. Okay, now we are in the Ansys meshing mode and we have our geometry. You will see the name selection parts here, and the geometry has imported successfully here. So now we are going to work on this mesh part. As you can see here, we need 100 intervals for mesh in the X direction and 5 intervals on the Y direction for this inlet and outlet. So to specify the number of selection, we need to select this mesh, right click on it and insert sizing. So I will select sizing first. We are going to work with geometry selection. So I will select click here, and then I will select this vertical line first, inlet, and then hold the control key and select this outlet together, press and apply, and we'll change this default setting, interval size, to number of divisions, so you can specify the number of mesh in this selected surfaces. So I will change it to 5 number of division. You can also select this uh, box here if you want to work a parametric and grid study for your generated mesh. You can see the first video of conduction. So in this video, I'm not going to use this parametric analysis. So I just select these 5. And then again, for these 2 horizontal lines, I will right click on the mesh, insert sizing. And this time, I will select this center line and this wall together with holding the control key. Click on apply, change this element size to number of division, and change this one to 100. So now we have 100 divisions on these 2 horizontal. So if I generate actually the mesh here, uh, you will see that I'm just going to show some things that we are going to consider in our generation. Mesh. So if I just right click here and generate the mesh, you will see we don't have a structured mesh like this one. It is going to apply these two sizing with 5 divisions in vertical and 100, but it's not a structure mesh. So we need to apply something else here. I will first right click on the mesh, clear the generate data. To do so, we need to define something for face meshing. So I will select this face meshing. And in the geometry, I will select this surface here, use apply button, and just check this one. It should be a mapped mesh, and it should be a quadratic mesh, quadratic method for this one. And again, if I right click here and generate the mesh, you will see this time we will have a structured mesh. But if you look in details, you will see the size of the meshes are not the same from left to right. So we need to change one other parameters to have the same size mesh. So to do so, first I will right click and clear the generate data. Press on yes to clear all the data. Press zoom to fit. So for this edge sizing, if you see here, there's an option growth rate, which in the default mode, which is a 1.2 here and here also. So if I change this default setting to 1 for this one, and also for this one, change this one by clicking and press a number. Then again, if I go and generate the mesh, and also you need to change this behavior from soft to hard, and also for this edge. So I will change this to hard, and then right click on the mesh and then generate the mesh again. And this time you will see the size of the element in this direction are all the same here. So you can also check some statistic here at the end of the mesh when you click here on the mesh. So under this statistics, you can open this one and you will see the number of elements here is 500, which means this 5 multiplied by 100, which is 500. So now the mesh is ready to export to Ansys Fluent. So to do so, if we go to workbench, you will see this is not the updated mesh, still it's not updated. So you can just simply click here on the mesh, right click, and then use this button, update. So this generated mesh will be sent to workbench, and you will see it has been updated now. I can close this Ansys Meshing. If you forgot to update the mesh with the Fluent Ansys Meshing, so you can just simply right click here and update this task here. So now it is time to open the Ansys Fluent. So I will click here, the launcher will be open. It's a 2D dimension. I will select on the double precision and change the number of processors to 4. But before start, I will just cancel this one and just press save the project to save this project. So, and I will open this setup again by double clicking, select double precision for number of processors and start the Ansys Fluent. Okay, so now the mesh has been imported here in Ansys Fluent. So we can have a look. We have different types of arrows here when you get your mesh inside the Ansys Fluent, and this is indicate that this boundary is the inlet boundary condition, and this red one is the outlet boundary condition. You can actually hide these boundary markers by these tools here by clicking on it. So here also I can check the mesh, go under this domain mesh and check, perform mesh check here. So you will see some information regarding your mesh. You can check this minimum volume of the mesh, which is a positive value. If it's minus value, so there's an error in your mesh, so you need to modify it. But in this case, it's okay. I can also get some information like this size. I go to info and size. You will see the number of cells as we checked in Ansys Meshing also. It's 500 cells, the number of cells in this domain. Okay, and in Ansys Fluent, you can use these tools for zoom in, zoom out, fit to window, and also use the middle bottom of the mouse to zoom in out. Hold the control key and with the middle bottom of the mouse, move your geometry. In this case, first I will use this fit to window. Then I can use this box selection zoom like this one. I will click and create a box, so you can zoom in a part of your domain in this graphics window. So that is for zoom in and zoom out. Move the geometry, rotate it, so you have some tools here. We can also go to the outline view first and check the cell zone, which is a fluid zone. Also the boundary condition. I have inlet here, one inlet, which is this one, one internal, which is this fluid here, one outlet, and two walls boundary conditions. Okay, for this center line, I will just change this center line type from the wall by right click here and change the type to axis. So you have different options to change this boundary from wall to those ones, but I will select the axis. So you will see these center lines are now under the axis boundary condition. So if I open it, so it's just the axis and there's no option to change or no settings. And then in the task page, I will go to the task page. So it's the solver is a pressure based and it's a steady simulation. And for the 2D space, I can select the axisymmetric. So this is the axisymmetric actually geometry, and this is half of the our geometry. And if I go to the scale here, you will see the minimum and maximum of your domain, which is here is 0 to 8 meter from here to here. And the minimum and maximum y value is between 0 and 0 0.1, 0 here and 0 0.5, which is the radius of this pipe. I can close this one. And now, as this is a laminar flow, I can go to the models here and actually use the laminar flow here. So I can double click on the Viscous model. The default setting is the SST K omega turbulent models, but I'm going to change this one to laminar because the Reynolds number in this pipe is just 100. So this is a laminar flow. I will change this one. I will keep this energy off because we are not going to analyze the heat transfer in this pipe. After that, I will go to the material, and under the fluid, I'm going to change some of the properties here. So in the problem specification, you can see the density is 1 kilogram per square cubic meter actually, and the viscosity is 2e minus 3 kilogram per meter second. So I can change the density to 1 and this one to 2e minus 3. Then I will select this change and create. So this value will be changed and I can close this air here. Then next I can go to physics to check actually this pressure, atmosphere pressure. So if you go to the physics, you can use this operation condition. I will keep this default value in the Pascal unit, which is equal to 1 atmosphere for this operation. And then I will just click OK. Now it is time to go to boundary condition. Before that, I will just go and check this fluid. I will double click on this fluid surface. I can change this name to fluid, for example, and you will see the air has been selected in the material, which is the only fluid that we have in this problem, in this Ansys Fluent. Now I will select apply, close, as I have changed this fluid name, so I can display again the mesh here and display, close this one. Now it is time to go through the boundary conditions. First of all, I will open the inlet boundary condition, which is the velocity inlet here. I will open this one by double clicking on it. Okay, so for velocity inlet, it is 1 meter per second. So here in this tab, momentum tab, I will change this velocity magnitude to 1 meter per second and apply here and then close this window. So next is the outlet boundary condition. Double click on this outlet, which is a pressure outlet boundary condition. I will keep this one as a gauge pressure. The absolute pressure at the outlet is 1 atmosphere. Since the operating pressure is set to 1 atmosphere first, so the gauge pressure actually is the outlet is equal to outlet absolute pressure minus operating pressure, which means it is equal to 0. So I will keep this gauge pressure to 0. Apply again and close. And the last boundary is the wall, so I will double click on the wall here. So only this momentum tab is active, and I don't need to change anything. It's a stationary with no sleep boundary condition. So I will close this window also. So now it is time to solve this problem. Okay, so to start to solve the problem, we need to change some settings or check some settings maybe. So in the method under the solution, I can double click here. I will keep all this default setting, just be sure that this momentum is selected. I mean, it's a second order upwind for the momentum. So for this pressure, I will select the standard. And for this pressure velocity coupling, I will change this couple to simple. So I will keep these ones as like this. I will change actually these settings to this ones you can see here. And now it is time to give some initial values to start the problem uh, actually here. But before initialization, I will go to the monitor and open the residual window here for all the equations, quantity, continuity, x velocity and y velocity. All the values are 0.001. I will decrease this value to 1e minus 6 for all this value. So I will copy and paste here. Just be sure all of this checkbox has been checked, and also you have this plot and print to console. So I will press on OK to close this window. Now I can go to initialization tab. I will select the standard initialization. Then here from compute I will select the inlet. So you will see this axial velocity initial value change to 1, and the gauge pressure and radial velocity are 0. So now I can press on initialize and then wait for a few seconds. Okay, now I can actually go to file and save this file if you want, but as I'm working in the workbench, I don't save the file. I just go directly to the run calculation. And just as a reminder, all of these tasks that I've done here in this tree method, you can go in these tabs at top and do the same process like this run calculation as I'm doing here. So I can go here in the under the solution, for example, and change these values here. So I will enter 100 number of iterations, and then I can start the calculation. So I will press on the calculate, and so we can wait and see the residual plot after a few seconds here. It's start to initialize the values and start running the problem. So the calculation has been completed, and as you can see here, solution is converged after 40A. So I will click on OK, go to the residual, scale the residual plot, and so the residual fall below the specified convergence criterion of 1e minus 6 in 48 iterations, as you can see here in this plot. And these are representative of the continuity, x velocity, and y velocity. You can see here in this. So now it is time to go to post-processing step here for this laminar pipe flow. First of all, we will plot the variation of the axial velocity along this center line. But as you can see here, this is just half of the this pipe actually. So as we are working on the axisymmetric problem, we can show the other part of this pipe, I mean hold the pipe cross section. So I can go to the view tab, and under this display view, I will select this one. So if I in this mirror planes, if I select this center line and apply, so you will see now I have hold the domain, the cross section of this pipe here. I can close this one and use fit to window. So for this post processing, I will use hold the domain with this method. So now I'm going to plot the variation, the axial velocity along the center line. In this case, we can use XY plot. So I will go to the results tab here. You can also work in this uh, tree here, this in the outline view, but I'm going to work here. So under this plot, I will select this XY plot and use a new. So now I'm here in this window, solution XY plot. Okay, so first we are going to have the position on the X axis. So I will keep this one position on X axis, and the plot direction in the X direction. So I will keep this one as 1 and this one as 0. Here I will select the velocity, and I'm going to plot the axial velocity. So I will change this one from velocity magnitude to axial velocity. And I'm going to plot this one on the center line. So under these surfaces, I will select the center line, and now I can plot this XY plot here. I'm going to change this axis here. I will go to here, select the Y axis, and then the type of this format. For this format, I will change this type from exponential to float and keep to precision. Apply, close this one, save again, and plot again actually here. So this is the axial velocity in meter per second, and this is the position. It means that this is the whole length of this pipe actually here. You will see after uh, after a few actually distance from the inlet, the velocity reached to a constant value, which is this point is the actually the fully developed part of this. I mean, after this length of the pipe, the flow will be fully developed in this area. Then the velocity in the center will be actually constant, remain constant here. So in a summary for this graph, actually we can see that the velocity reaches a constant value beyond a certain distance from the inlet here. So this is the fully developed flow region. You can see this XY plot here under the XY plot. You can also change this name to axial velocity, for example, if you want, and save it. So it will change to axial velocity. You can also save this data to the text file if you if you click on the write to file. So this button will be changed to write. So you can write here, and then this is for axial velocity data. You can save it. I will uncheck this one and save it again. Close this window for now. Also in this plot, I can show you something else here. For example, so in this plot, you can go to the axis and change some values. For example, if you are going to zoom a little bit more on some specific area, so you can go to the axis here, and for this X axis, I'm just going to limit this position between some specific area, for example, between this 1 and 3 meter. So I should just uncheck this auto range, and in this range I will select 1 to 3, for example, for this X value. And if I apply this one and save the plot again, you will see the position is between 1 and 3 meter in this plot, and you will see it's now going to be constant value in this area. We can also turn on the grid lines to help estimate where the flow becomes fully developed, for example. So in this X direction, for example, if I select the major rules and apply here for this X, for example, and save again, you will see you can see these grid lines. I can add also for the Y direction the majors, apply and save. So you will see these grid lines in the X and Y direction. For this Y-axis also, I will uncheck this auto range and change this one to 1.8, and for maximum I will select 2, apply, and save and plot. So you will see in a more zoomed area in the variation of the velocity axis in this selected area. You can also use these minor rules for both X and Y. And now we can see that the fully developed region starts at around x equal 3 meters, and the center line velocity in this region is roughly 1.92 meter per second. Okay, now I will close this windows here. You can also save this plot as a picture, for example, if you want. So for this case, you can go here in this toolbar here and save your picture, save picture, click here. So you can select different formats like PNG or JPG. So I will select this PNG for now. Also, you can change the resolution. Here I will select, for example, 4K resolution for this graph. And you can also have the white background or this dark background, for example. So first I will uncheck this one, this white background, and then save the plot. Okay, so this file will go to your project actually. In this project Laminar Pipe Flow DP0FFF, and in the MEC part. So I have this XY plot. I can open this plot here. This is a 4K resolution. So you will see this graph as it is, axial velocity, exactly the same as we have in the graphic window of this Ansys. Now I can close this window also. Now let's go to create a coefficient of screen friction XY plot. So to do so, I'm going to go to reference values here under the results. I will open this window here. I will select the inlet for this compute from, and we need to check, for example, some parameters like density, which is should be 1 kilogram per cubic meter, and the velocity should be 1, which is 1 meter per second here. You have this value from the inlet boundary condition, but you also can change these values by typing your desirable values. So I will keep this one here, like this one. Again, we can go to the XY plot, create a new XY plot, or change the previous one. So for this case, I'm going to create a new XY plot. I will call this one as the skin friction. I will keep this position on x-axis, keep this one for x, and then change this y-axis function from pressure to wall flux. The skin friction coefficient is under this wall flux, so I will select this one as well. So this time I should use the wall because this is a skin friction coefficient. I will select this wall. I can go to the actually here. If you are going to change something before that, I will press on the save plot to have this plot here. So if you are going again to add, for example, major rules or minor rules for X and Y, I will select apply for, I will do the same for both X and Y axis, save and plot. So I will close this value. And as you can see, the fully developed region is reached at around 3 meters here, roughly, and the skin friction coefficient in this region is around 1.54, for example. So I can also use this write to file, save, and call it as a skin friction. Click skin friction and press on OK. Close this window this time. So I will close one of these. So I have opened two different plots here. If you are going to see those two beside each other. So you can right click on one of these tabs here, the window, and use sub window view. So you have these two beside each other, and maybe, for example, you can adjust these two windows to see beside each other. I will move a little bit down like this, increase the size. And now I have these two values beside each other, but this is between 1 and 3, and this is in the holder domain. So this is the way that you can see all the opened graphic window beside each other. I will switch to the tab view. Then we will next plot the velocity at the outlet as a function of the distance from the center of the pipe. To do this, we have to set the y-axis of the graph to be the y-axis of the pipe, actually the radial direction. Okay, so we need a new xy plot. I will select this one, new one, and for the name, I will call it outlet velocity. But this time, I'm going to plot in the y direction, in the radial direction. So first I need to uncheck this position on X and change it to Y-axis. And this time the plot direction is radial, so I will change this X to 0 and Y to 1. So this time you will see you need to select the x-axis function actually here. So I will go to select the velocity and axial velocity again here, but this time I'm going to define this plot on the outlet. I will keep this default for now here for the axis, and I'm going to plot this one. We'll go to the axis again for the X. I will select major and minor rows. Go to Y, major and minor. Click apply. Close this one. Save. So I need to change some of this value. I will go to the axis. For the y-axis, I will change this exponential to float with 2 precision, for example. Apply, save. It's done. But for this auto range, I'm going to show this graph between 0 and 0.1. So I will change this auto range and change this maximum to 0.1. Apply and save the plot again. So now it is in this range actually. And now I'm going to write this file, the data for this file. I will call it as profile.xy for xy plot. Press on OK. So to see how the velocity profile changes in the developing region, let me add the profiles at x equals 0.6 meter and x equals 0.12 meter to the above plot. So first I'll create a line at these two options, x equals 0.6 and then x equal 0.12. So I will close this graph for now. So you see I have 3 graphs. But for this purpose, I'm going to use one tool to create 2 lines. First, I will go to the surface and I will use this option, line or rake. So I will select this one and this window will be open. So if I just display one time the mesh, actually here I will display this mesh. So I'm going to first create the line 1 roughly here, for example, in the x equals 0.6. So I need to define 2 points here, point 0 and point 1 for the x value, it is in 0.6 and the y is 0 here, for example. And for this one, 1 point should be here at top, so it is 0.6, and the height, as we know, it is 0.1. I will call this one as a line 1. So I will create this line here. You will have this one here also, and also in the mesh you will see this line now here. So I will select this one. You can see I've created this first line here. Similarly, I will create another line. So I will go to the line rake again. I will call it as line 2, for example. And this time I will change this x0, x point 0 and point 1. So I will change this one to 1.2 and y is 0. And for this one, so it is roughly here, 1 point here, and the next point will be on top of this one. So in the x direction, it is 102, and here it's 0.1. So I will click here to create the new line, and I have this line also here. So I will select this one. So you will see two new actually line has been created here. This one and this one. So I can close now this to 1, and now we can plot the velocity profile as x 0.6 and x 1.2 actually here. Let's go to the xy plot again, new xy plot here. So the same process as previous plot. So I will go to the y-axis. This one changed to 0 and then 1. Here velocity, axial velocity, but this time I will select outlet and line 1 and 2, 3 together, and I can go to actually here, for example, apply, and the same process. For the x-axis, I will select float to precision, for example, apply, save and plot. So we have this plot here. I think I can change the y value also from exponential to float, and then I think it seems better. So now I have this one, this xy plot. I can change this name to axial velocity all lines. Save it again. So this profile and downstream is fairly close to fully developed profile at outlet. If you redo this plot using the fine grid result in the next step, you will see that this is not actually the case. The coarse grid used here doesn't capture the boundary layer development properly and underpredict the development lengths. Okay, now I will close this one, and I'm going to show the velocity vectors. So let me plot the velocity vectors for the entire domain to see how the flow develops downstream of the inlet. To create a velocity vector, here under this graphics, I will select a new vectors contour here. I will call it as velocity vector. So I will keep this velocity here, and then select this interior surface, which is our fluid. So I can select this one. So this velocity vector will be displayed on these surfaces. I can change the position of this legend here, and also can zoom a little bit here. in the region near the inlet. So you can see this velocity vector. So I can decrease the scale of these vectors to, for example, 0.4, save and display to have a better view here. Again, change this one to here. As we used hold the domain, I used the mirror planes, center line as a mirror plane. So I have this velocity vectors to hold the pipe here, and you can see this velocity vector. So the velocity vectors provide a picture of how the flow developed downstream of the inlet. So as the boundary layer grows, the flow near the wall is retarded by viscous friction. Note the sloping arrows in the near wall region close to the inlet here. You can see. So this indicates that the slowing of the flow in the near wall region results in an injection of fluid into the region away from the wall to satisfy mass conservation. Thus, the velocity outside the boundary layers increases. So by default, one vector, actually each of these vector is drawn at the center of each cell. Maybe we can see with the draw mesh. So let's see together. I will click here on the draw mesh and display, and this time save again. I will move this one at top, and you can see each of these vectors is in the center of each of these cell. So now I can close these two window here, and then to see like this, we can go check here near the outlet. This is our fully developed region in this pipe. So to have a better results, you need to refine mesh. So if you are going to do so, you can go some step backs to Ansys Meshing, Ansys Meshing actually, and change the size of the mesh and the number of this mesh here to see the new results and compare with this results. So for now, I can actually close this Fluent. You will see all these steps has been done here. I can save the project also here in the workbench, this Laminar Pipe Flow. So everything has been done, and I can actually close this Ansys Fluent and also workbench for this. So that wraps up our second 2D tutorial in the Ansys Fluent Academy Beginner CFD series. In this video, we create the geometry in a SpaceClaim, set up the mesh in Ansys Meshing, define our boundary condition, and ran the simulation to observe how the velocity profile develops and reach a fully developed laminar flow. If you haven't already, I recommend watching the earlier videos in this series to make sure you don't miss any foundational actually steps. And please stay tuned. In the upcoming tutorials, we will continue building on this concept with more complex geometry, boundary conditions, and flow regimes. If you found this helpful, please give it a like, subscribe to the channel, and turn on notifications so you don't miss the next lesson. Thanks for watching.